Hello there, and welcome back to the Sleep Science. Tonight, you're standing beneath a sky that looks perfectly calm, washed in late afternoon gold. The sun hanging there like a polite, glowing coin. It feels steady, reliable, ancient, the kind of celestial object you assume has its life together. And yet, 93 million miles above your head, that enormous sphere of plasma is twisting, snapping, and rearranging its magnetic guts in ways that would make your phone's battery anxiety look adorable. You probably won't survive this, at least not without electricity, satellites, or the internet. But let's not panic just yet. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, tell me where you are in the world and what your local time is. I love picturing this quiet network of night owls orbiting the same star. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your head upward, and imagine peeling back the blue of the sky. The sun looks smooth from here, but up close it's a boiling ocean of charged particles. Hydrogen atoms fuse into helium in its core, releasing energy that takes thousands, sometimes hundreds of thousands, of years to reach the surface. That's a mainstream astrophysical fact. The sunlight warming your face today began its journey long before humans were painting on cave walls. So, technically, you're enjoying very vintage light. Solar antique. No refunds. Scientists have always watched the sun. Galileo famously sketched sunspots in the early 1600s, carefully projecting the solar image, so he wouldn't fry his retinas. Please don't try that at home. The Renaissance was wild enough. But right now, in this era of satellites and streaming services, researchers are watching more closely than ever before. Not out of simple curiosity, but because the sun seems to be entering a particularly lively phase. You imagine the surface not as a flat disk, but as a restless skin. Great loops of magnetism arch up and sink back down. The sun rotates roughly once every 27 days at its equator, a confirmed observational fact, but it spins more slowly at its poles. This differential rotation twists magnetic field lines like rubber bands. Eventually, they snap. When they do, energy bursts outward in flares and coronal mass ejections. Terms that sound like indie rock bands, but are decidedly less chill. Right now, solar activity is ramping up as we move through an 11-year solar cycle. These cycles have been tracked since the 18th century, when astronomer Samuel Heinrich Schwab noticed that sunspot numbers rise and fall in a predictable rhythm. That rhythmic swelling and quieting is a mainstream cornerstone of solar physics. But this current cycle has already surprised researchers by intensifying faster than many predictions suggested. It's as if the sun skipped its morning coffee and went straight to espresso. You picture scientists in observatories and control rooms, eyes fixed on monitors filled with ultraviolet images. The sun in those wavelengths doesn't look yellow or friendly. It looks electric blue and violent, marble with flares that blossom like cosmic bruises. Space agencies worldwide, NASA, ESA, JAXA, have launched missions specifically to study solar behavior in unprecedented detail. The reason is simple. Modern civilization is tangled up in delicate electronics. The sun's moods now matter more than ever. Here's something quirky. In the 1800s, before we understood solar physics, some scientists speculated that sunspots were holes in the sun revealing a cooler, possibly even inhabited interior. Yes, there were serious discussions about potential solar life. Tiny sunspot salamanders, perhaps just vibing in nuclear fusion. Historians still argue whether those ideas were metaphorical musings or genuine hypotheses. But either way, it's comforting to know that even brilliant minds occasionally looked at a star and thought, maybe there's real estate in there. As you breathe slowly, imagine standing on the surface of the sun. Hypothetically, because you would vaporize instantly, the surface temperature averages about 5,500 degrees Celsius, a widely accepted measurement. But above it lies a corona, the sun's outer atmosphere, which can reach over 1,000,000 degrees Celsius. That's not a typo. The outer layer is hotter than the surface below it. It's one of the great puzzles of astrophysics. Heat behaving badly. Scientists are watching closely because subtle changes in magnetic patterns can precede massive solar events. These events don't just create pretty auroras. They can disrupt radio communications, GPS systems, and power grids. In 1989, a geomagnetic storm caused a blackout across Quebec, leaving millions without electricity for hours. That's not ancient history. That's recent enough to remember VHS tapes. You picture the sun as a temperamental orchestra conductor, waving magnetic batons. Sometimes the music is gentle, a steady hum of solar wind washing over Earth. Other times it crescendos into chaos. And the thing is, we're now dependent on technology that didn't exist during most of recorded solar history. For thousands of years, a solar storm meant brighter northern lights and maybe confused pigeons. Today, it means grounded flights, satellite glitches, and mildly panicked group chats. There's also the matter of prediction. Scientists can forecast general trends in the solar cycle, but pinpointing the exact timing and intensity of a flare remains notoriously difficult. The sun's magnetic field is a three-dimensional labyrinth constantly evolving. Historians still argue whether early observers underestimated solar variability because of limited instruments, or whether the sun itself is becoming more erratic in subtle ways. The debate keeps conferences lively and coffee consumption heroic. You feel the scale of it now. That bright disk isn't just scenery. It's a dynamic, living engine of plasma physics. And as humanity grows more technologically intertwined, the margin for surprise shrinks. Watching the sun has shifted from academic fascination to planetary necessity. The air around you feels softer as you imagine solar observatories tracking each flicker. Instruments measure X-ray flux, magnetic flux, ultraviolet emissions. Data streams in constantly. Terabytes of sunlight translated into numbers. Somewhere, an algorithm hums quietly, trying to guess whether tomorrow will be calm or electrically dramatic. And above you, the sun continues to glow with deceptive serenity. A star in midlife. Stable, mostly. Predictable, sometimes. Harmless, until it isn't. You keep gazing upward, knowing that this quiet warmth hides a restless heart, and that the story of why scientists are watching so closely is only just beginning to unfold. You remain there beneath that deceptively peaceful glow, but now you begin to sense a rhythm pulsing through it. A slow inhale and exhale that stretches across more than a decade. The sun, for all its fiery chaos, is a creature of cycles. About every 11 years, its magnetic personality flips, resets, and builds again. This is a solar cycle, first systematically documented in 1843 when German astronomer Samuel Heinrich Schwab published his discovery that sunspot numbers wax and wane in a regular pattern. It was one of those quiet scientific realizations that didn't make fireworks at the time, but it changed how you understand the star above you. You imagine the sun keeping a cosmic calendar. Year by year, sunspots begin to appear more frequently, clustering in bands north and south of the equator. They multiply, peak, then gradually fade away until the surface looks calmer again. This peak is called solar maximum. The low is solar minimum. Simple names for dramatic shifts. During solar maximum, the sun's magnetic field becomes tangled and complex, like a drawer full of headphones you swore you wrapped neatly. Right now, you're living through solar cycle 25. Officially, it began in December 2019, when scientists confirmed the previous minimum had passed. Predictions suggested it might be relatively mild, similar to the last cycle. But as the years ticked forward, sunspot counts began rising faster than expected. By 2023 and 2024, activity levels were exceeding many early forecasts. It's not apocalyptic, but it's energetic enough to make solar physicists lean forward in their chairs. Here's the mainstream fact anchoring this. Each 11-year cycle is actually part of a 22-year magnetic cycle. At the end of each 11-year span, the sun's magnetic poles flip. North becomes south, south becomes north. After another 11 years, they flip back. So if you could fast forward a compass needle on the sun, you watch it reverse direction like it's indecisive at a crossroads. Historians still argue whether the sun cycles are perfectly regular or subtly chaotic over centuries. There have been prolonged lulls, like the Maunder minimum from about 1645 to 1715, when sunspots became exceedingly rare. This period coincided with the coldest part of the Little Ice Age in Europe. Rivers like the Thames froze more frequently, and winter festivals were held on the ice. Some scientists propose a connection between low solar activity and cooler global temperatures, while others caution that volcanic activity and internal climate variability played larger roles. The debate continues, polite but persistent. You picture 17th century astronomers peering through primitive telescopes, puzzled by the sun's quiet face. They had no satellites, no magnetograms, just careful sketches and patience. And yet their observations laid the groundwork for understanding that the sun is not static. It breathes in decades. A quirky tidbit drifts into view. During the Maunder minimum, some people interpret the lack of sunspots as a sign of divine favor or cosmic stability. Others saw it as an omen. It's funny how humans can look at the same star and project either reassurance or dread onto its freckles. Now, bring your attention back to the present cycle. Solar maximum isn't just about more spots. It's about more flares, more coronal mass ejections, more geomagnetic storms. In May 2024, a series of powerful solar storms triggered widespread auroras visible much farther south than usual, into parts of the United States and Europe that rarely see such displays. Social media lit up with pink and green skies. It felt magical, romantic, slightly apocalyptic, but in a photogenic way. You can almost see the aurora shimmering above you now, curtains of charged particles dancing as they collide with Earth's magnetic field. That spectacle is the beautiful side of solar maximum. The less glamorous side involves increased radiation exposure for satellites and astronauts, degraded radio signals, and subtle atmospheric expansion that increases drag on low Earth orbit spacecraft. As solar activity ramps up, Earth's upper atmosphere heats and swells. This increases friction on satellites, causing them to lose altitude faster than expected. In 2022, for example, SpaceX lost dozens of Starlink satellites after a geomagnetic storm increased atmospheric drag shortly after launch. That's not theoretical risk. That's expensive space confetti. You feel the tension in this rhythm. The cycle is predictable in broad strokes, but its intensity is harder to pin down. Scientists use mathematical models and historical data to forecast each upcoming maximum. Panels convene. Graphs are drawn. Confidence intervals are calculated. And yet the sun sometimes decides to freelance. There's also speculation about whether recent cycles are part of a longer-term modulation. Some researchers study patterns spanning centuries, using tree rings and ice cores to infer past solar activity through isotopes like carbon-14. These records suggest the sun has episodes of unusually high or low activity, lasting decades. Historians still argue whether we are heading toward a grand minimum or simply experiencing normal variability amplified by better instruments. Imagine standing in a control room filled with live solar imagery. Bright active regions rotate into view over the limb of the sun. You know that in a few days, those regions will face Earth directly. If they unleash a flare, it could send radiation our way in 8 minutes. The time it takes light to travel from sun to Earth. 8 minutes. That's less time than it takes to decide what to watch before falling asleep. And yet, despite the drama, there's comfort in the cycle. The sun has been doing this for billions of years. Long before humans built power grids or worried about satellite constellations, magnetic fields were twisting and flipping on schedule. You're witnessing just one crest in a long, rolling tide. The rhythm continues minimum to maximum, quiet to stormy, north to south and back again. Scientists watch because the stakes are higher now, but also because each cycle is a fresh opportunity to test theories, refine models, and maybe finally answer why the star's magnetism behaves the way it does. Above you, the glow remains steady to your naked eye. No visible flipping. No obvious crescendo. Just warmth. But beneath that golden surface, the cycle is climbing, building toward its peak like a symphony tuning up backstage. And you, small and thoughtful under its light, begin to understand why no one in solar physics is looking away. The rhythm of the cycle carries you forward, and now you begin to notice the freckles. At first, they seem insignificant, tiny dark blemishes scattered across the sun's blazing face. But as solar maximum approaches, they multiply, they cluster, they stretch into tangled groups that look almost deliberate, as if your star has decided to accessorize. These are sunspots, and despite their moody appearance, they're not holes or scorch marks. They're cooler regions. Cooler meaning about 3,500 degrees Celsius instead of the usual 5,500. On the sun, that temperature difference is enough to look dark by contrast. It's like calling lava chilly, because it's slightly less lava. The mainstream science is clear. Sunspots are caused by intense magnetic fields punching through the sun's surface, suppressing convection. Normally, hot plasma rises, cools, and sinks in a constant boil. But strong magnetic flux tubes inhibit that motion, trapping slightly cooler plasma in place. The result is a darker patch, often larger than Earth itself. Yes, one spot can swallow your entire planet with room left over for the moon as a garnish. You imagine standing on the sun's surface, again hypothetically, because you vaporized before finishing the sentence, and watching these magnetic regions churn. Around each sunspot, bright loops of plasma arc high into the corona, tracing invisible magnetic field lines. These loops can persist for days or weeks, evolving as the sun rotates roughly once every 27 days at the equator. So a particularly active region can swing into view, face Earth, rotate away, and then reappear 2 weeks later like a dramatic celebrity making a second entrance. Sunspots aren't random splatters. They follow a pattern known as a butterfly diagram. Over the course of a solar cycle, new sunspots appear at mid-latitudes, around 30 degrees north and south of the solar equator. As the cycle progresses, the spots emerge closer and closer to the equator, forming wing-like distributions when plotted over time. This pattern has been observed for over a century. It's one of those elegant pieces of astrophysical choreography that makes you forget the sun is essentially a giant nuclear reactor. Historians still argue whether early sunspot observers fully grasped their significance. In 1610, Galileo and other astronomers independently documented sunspots, challenging the prevailing Aristotelian idea that heavenly bodies were perfect and unblemished. The discovery wasn't just scientific. It was philosophical dynamite. The heavens had flaws. The cosmos wasn't polished marble. It was dynamic, messy, alive. There's also a quirky footnote from the 19th century. Some amateur astronomers believe sunspot cycles influenced everything from wheat prices to human behavior. One economist even proposed correlations between sunspot activity and financial panics. Imagine blaming your bad stock portfolio on solar magnetism. It wasn't me, it was the star. While modern research has found no robust link between sunspots and market crashes, the attempt reveals how eager humans are to tie cosmic rhythms to everyday life. But sunspots do have real terrestrial consequences. They are the birthplaces of solar flares and coronal mass ejections. The stronger and more complex the magnetic fields in a sunspot group, the greater the potential for explosive releases of energy. Scientists classify active regions by magnetic complexity. Simple bipolar groups are less threatening, while tangled, multipolar configurations raise eyebrows in control rooms. Right now, during this rising phase of solar cycle 25, sunspot counts have surged beyond initial predictions. Some months have recorded the highest numbers in over 2 decades. This isn't unprecedented, but it is enough to suggest that the sun may be more vigorous than forecasted. You can almost feel solar physicists quietly updating their models. Try not to spill coffee on the keyboard. Picture a massive sunspot group rotating into Earth-facing position. It spans tens of thousands of kilometers. Dark umbra at the center, lighter penumbra feathering outward. Around it, magnetic field lines twist like overstretched springs. If those lines reconnect suddenly, a process called magnetic reconnection, energy stored in the field converts into heat, light, and kinetic force. A flare erupts. Radiation blasts outward at light speed. You wouldn't see it with your naked eye, but satellites monitoring X-ray flux would spike instantly. Alerts would ripple through space weather centers. 8 minutes later, the radiation reaches Earth. If it's strong enough, it can ionize the upper atmosphere, disrupting high-frequency radio communications. Pilots flying polar routes sometimes reroute during intense events, not because the sky is on fire, but because invisible ionization makes radio chatter unreliable. There's an almost poetic irony here. Sunspots, which look like imperfections, are actually signs of magnetic strength. The darker the patch, the more intense the field. Beauty standards clearly don't apply to stars. Scientists also study the magnetic polarity of sunspot pairs. Typically, one spot in a pair has a north polarity and the other south, aligned according to Hale's law, discovered in the early 20th century. With each new solar cycle, the leading spot's polarity flips in each hemisphere. This alternating pattern is key evidence of the sun's deeper magnetic dynamo at work. It's not random chaos, it's structured turbulence. And yet, the dynamo mechanism itself is still not fully understood. Deep beneath the surface, plasma flows in complex patterns, influenced by rotation and convection. These flows stretch and fold magnetic fields in ways that models are still struggling to replicate precisely. Historians still argue whether our current dynamo theories are fundamentally complete or missing a subtle layer of physics hidden in the sun's interior shear zones. You imagine the sun as a living map of magnetism, its freckles marking stress points in a vast, glowing organism. Each spot is a symptom of deeper currents. Each cluster hints at energy waiting to be released. From Earth, though, it's just a bright circle you're told not to stare at. Calm, consistent, ordinary. But now you know better. You know those dark specks are warnings and wonders at once. Magnetic knots in a star that sustains your entire biosphere. And as their numbers climb, as the butterfly wings drift toward the equator, you understand why observatories around the world are counting every single one. Because each spot is a story, and some of those stories end with storms. As the sunspots multiply and drift across that blazing surface, you begin to sense that they are not the main event. They are merely the stage. The real drama unfolds above them, in the sun's atmosphere, where invisible magnetic field lines stretch, twist, and occasionally snap with theatrical flair. You rise gently in your imagination, floating upward from the visible surface, the photosphere, into the chromosphere, a thin reddish layer glimpsed during total solar eclipses. Above that lies a corona, the sun's outer atmosphere, extending millions of kilometers into space. It's faint to your eyes but ferocious in temperature, soaring past 1,000,000 degrees Celsius. Yes, again with the outer layer hotter than the surface paradox. Solar physics loves a good plot twist. Here, storms are born. A solar flare begins with magnetic reconnection. Picture two tightly wound magnetic field lines crossing paths, stressed and distorted by the sun's differential rotation. When they realign into a lower energy configuration, the excess energy doesn't politely fade away. It explodes outward. In seconds and minutes, a flare can release as much energy as billions of hydrogen bombs. That's not poetic exaggeration. It's a mainstream scientific estimate based on measured energy outputs. You don't hear anything, space is silent, but you see a brilliant flash in ultraviolet and X-ray light. Instruments aboard satellites like NASA's Solar Dynamics Observatory capture these bursts in exquisite detail, imaging the sun in multiple wavelengths. To human eyes, it looks like a sudden, blinding bloom. To scientists, it's data. Flux levels, duration, classification. Flares are ranked by strength, A, B, C, M, and X class, each step representing a tenfold increase in energy. An X-class flare is the heavyweight champion. When one erupts, space weather forecasters sit up very straight. It's the astrophysical equivalent of your calm neighbor suddenly buying fireworks in bulk. But flares are only half the spectacle. Sometimes, the magnetic upheaval launches a coronal mass ejection, a CME. Imagine billions of tons of solar plasma hurled into space, embedded with magnetic fields, traveling at speeds that can exceed 1,000,000 miles per hour. Unlike the near-instantaneous radiation from a flare, a CME takes 1 to 3 days to reach Earth. It's less like a lightning strike and more like a solar hurricane barreling across interplanetary space. The mainstream physics is clear. CMEs are major drivers of geomagnetic storms. When their magnetic orientation opposes Earth's magnetic field, they can reconnect with it, transferring energy into our magnetosphere. This interaction can intensify auroras and, in severe cases, disrupt technology. You hover alongside one of these ejections in your mind. It expands as it travels, a vast bubble of magnetized plasma. Spacecraft positioned between the Sun and Earth, like the Discover satellite at the L1 Lagrange point, act as sentinels, measuring incoming solar wind conditions. They provide about 15 to 60 minutes of warning before the bulk of a CME strikes Earth's magnetic field. Not a huge amount of time, just enough to send a flurry of alerts through space weather centers. Historians still argue whether earlier civilizations noticed subtle effects of solar storms beyond auroras. Ancient Chinese and Korean astronomers meticulously recorded unusual sky glows, some of which modern researchers interpret as intense auroral displays at low latitudes. Whether those events corresponded to massive CMEs is an ongoing area of scholarly detective work. There's also a wonderfully odd tidbit from 1859 during the famous Carrington Event, which we'll explore more deeply later. Telegraph operators reported sparks flying from their equipment, and some claimed their systems continued transmitting even after power supplies were disconnected, powered purely by geomagnetically induced currents. Imagine sending a message with electricity borrowed straight from a star. Victorian texting, but with more existential dread. Back in the corona, you notice something else. Towering loops of plasma called prominences. These can hang suspended for days, graceful and curved, held aloft by magnetic fields. Sometimes they erupt, contributing to CMEs. Other times they simply collapse back onto the surface, like a dramatic sigh. Scientists still debate the precise triggers that determine whether a magnetic configuration will produce a minor flare or a massive CME. Models simulate magnetic shear, flux emergence and helicity, the twistiness of field lines, but predicting the exact moment of eruption remains notoriously difficult. Historians still argue whether our forecasting challenges stem from insufficient data resolution or from deeper nonlinear chaos inherent in plasma physics. The sun, after all, is not a solid object. It's a churning sphere of ionized gas governed by magnetohydrodynamics, a term that sounds intimidating but simply describes the interaction between magnetic fields and conducting fluids. Plasma flows generate magnetic fields. Magnetic fields guide plasma flows. It's a feedback loop of cosmic complexity. And yet, from Earth, the sun continues to appear serene. You feel its warmth on your skin, steady and life-giving. No hint of the magnetic tempest roaring above its surface. That contrast is part of why scientists are watching so closely now. With modern instruments, they can observe storms forming in real time. They can measure shifts in magnetic topology before eruptions occur. They can compare current activity to decades of archived solar imagery. Each flare, each CME adds to a growing dataset aimed at one goal: prediction. Because while a solar storm is beautiful from 93 million miles away, it becomes consequential when aimed in your direction. You drift back down toward the photosphere, toward those dark sunspots that started this chain reaction. They seem quieter now, almost innocent. But you know better. Above them, the corona crackles with potential, storing energy in twisted magnetic fields like a coiled spring waiting for release. And somewhere in a dimly lit control room filled with glowing monitors, scientists watch those springs tighten, hoping to understand exactly when and how they will snap. You're still hovering in that invisible space between the sun and Earth, watching the aftermath of a flare ripple outward. The flash itself is over in minutes, but its effects move at the speed of light. 8 minutes after magnetic reconnection snaps high above a sunspot, a pulse of X-rays and extreme ultraviolet radiation slams into Earth's upper atmosphere. You don't feel it on your skin. You don't see it in the sky. But the ionosphere, the electrically charged layer of the upper atmosphere, reacts almost instantly. The mainstream physics is straightforward. High-energy solar radiation ionizes atoms and molecules in the ionosphere, increasing the density of free electrons. That sudden boost can absorb or reflect high-frequency radio waves differently than usual. The result? Radio blackouts, particularly on the sunlit side of Earth facing the flare. Imagine you're piloting a commercial flight over the Arctic. Polar routes are common for long-haul travel between North America and Asia because they save time and fuel. But they rely heavily on high-frequency radio communication. During strong solar flares, especially M-class or X-class events, airlines sometimes reroute flights to lower latitudes to maintain reliable contact. It's not dramatic from a passenger's perspective. You just land slightly later and wonder why your in-flight map looks shy. But behind the scenes, space weather forecasters are tracking solar X-ray flux in real time. There's even a formal scale from the National Oceanic and Atmospheric Administration, NOAA, for radio blackouts, labeled R1 through R5. An R5 event, the most severe, can cause complete HF radio blackouts on the entire sunlit side of Earth for hours. That's not science fiction. It's rare, but documented. And then there are satellites. You picture them circling quietly above. Navigation satellites, weather satellites, communication constellations. They exist in a delicate balance between gravity and velocity, wrapped in electronics that are sensitive to radiation. During intense solar flares, energetic particles can penetrate satellite shielding, causing temporary malfunctions known as single-event upsets. A bit flips in memory. A sensor glitches. Most systems are designed with redundancy, but the risk increases during heightened solar activity. Historians still argue whether the rapid expansion of satellite megaconstellations in low Earth orbit has outpaced our understanding of cumulative space weather risk. Thousands of small satellites now orbit the planet, and while individually resilient, collectively they represent a new level of exposure. The sun, indifferent as ever, does not adjust its behavior for our launch schedules. You descend closer to Earth's magnetic shield, the magnetosphere. Normally, it deflects a steady stream of charged particles known as the solar wind. But when a strong coronal mass ejection follows a flare, carrying a southward-oriented magnetic field, it can reconnect efficiently with Earth's field. Energy pours in. The magnetosphere compresses on the day side and stretches into a long tail on the night side. This is when geomagnetic storms ignite. One confirmed historical example stands out. In March 1989, a powerful geomagnetic storm collapsed the Hydro-Quebec power grid in Canada. Within 90 seconds, the system failed, leaving 6 million people without electricity for about 9 hours. Transformers overheated. Protective systems tripped. It wasn't the end of the world, but it was a sharp reminder that power grids can act like giant antennas for geomagnetically induced currents. You imagine long transmission lines stretching across continents. When Earth's magnetic field fluctuates rapidly during a storm, it induces electric currents in these lines. Transformers, designed for steady alternating current, can saturate under this unexpected load. In extreme cases, they can suffer permanent damage. And replacing a large transformer is not like swapping out a toaster. Some weigh hundreds of tons and require months to manufacture. There's a slightly quirky footnote from the early days of telegraphy in the 19th century. Operators sometimes experience mild electric shocks during geomagnetic storms. Papers reported auroras bright enough to read by at night, even in tropical regions. People were equal parts awed and unnerved. Imagine stepping outside in Havana and seeing crimson curtains ripple overhead, with no Instagram filter to explain it. Yet not all effects are disruptive. During moderate storms, auroras expand toward lower latitudes, delighting photographers and night owls. In 2024, strong solar activity produced auroras visible across much of the continental United States and parts of southern Europe. Social feeds filled with astonished captions. The sun had sent a storm, and Earth responded with color. Still, the unpredictability keeps scientists vigilant. Historians still argue whether our current infrastructure is adequately hardened against a once-in-a-century event like the 1859 Carrington Event. Some studies suggest a severe geomagnetic storm today could cause widespread, long-lasting outages. Others argue that grid protections and monitoring systems have improved significantly. The truth likely sits somewhere in between, better prepared, but not invincible. There's also the subtler effect of radiation exposure. During strong solar particle events, often associated with flares and CMEs, high-energy protons can reach Earth's vicinity. Astronauts aboard the International Space Station may retreat to more shielded areas. Even airline crews on high-latitude flights experience slightly elevated radiation doses during intense events. It's generally within safety limits, but it's monitored carefully. You begin to appreciate the layered choreography: flare, radiation pulse, CME, geomagnetic storm. Each step unfolds across different timescales: minutes, hours, days. Scientists watch solar observatories, particle detectors, magnetometers, and satellites in constant dialogue. And through it all, the sun shines as it always has, bathing your world in warmth. You step back mentally and feel the scale of dependence. GPS timing synchronizes financial transactions. Satellites guide ships through fog. Power grids hum across continents. So much of your daily life is quietly entangled with a star's magnetic temperament. When a flare erupts, it's not just a flash in the void. It's a reminder that you live downstream from a fusion reactor with moods. And so the watching continues, not because the sun is new, but because your civilization is. You drift now into the past, to a late summer morning in 1859, when the sun decided to make history. It's September 1st. An amateur astronomer named Richard Carrington is in his private observatory in England, projecting the sun's image onto a screen so he can safely sketch its sunspots. This was standard practice at the time. No sunglasses brave enough for direct staring. As he traces the outlines of a large sunspot group, he notices something extraordinary. Two intensely bright patches suddenly flare to life within the dark region. They shine for about 5 minutes and then fade. Carrington has just witnessed the first recorded observation of a solar flare. At nearly the same time, another astronomer, Richard Hodgson, independently observes the same flash. Neither man fully grasps the scale of what's unfolding. About 17 hours later, remarkably fast for solar material, a massive coronal mass ejection slams into Earth's magnetosphere. What follows is now known as the Carrington Event, the most powerful geomagnetic storm in recorded history. You imagine the skies that night. Auroras blaze far beyond their usual polar homes. Reports describe crimson and green lights visible in the Caribbean, in Hawaii, even near the equator in Colombia. In the northeastern United States, people reportedly wake in the early hours believing the sun is rising. Newspapers could be read outdoors at midnight by auroral light alone. It must have felt biblical, or extraterrestrial, or like the atmosphere itself had decided to put on theater. The mainstream historical record confirms that telegraph systems across Europe and North America malfunctioned dramatically. Operators received electric shocks. Sparks flew from equipment. Some telegraph lines continued transmitting messages even after being disconnected from their batteries, powered purely by geomagnetically induced currents flowing through the wires. Imagine unplugging your router and still getting Wi-Fi because the sun insists. One operator in Boston reportedly described sheets of flame erupting from his apparatus. It sounds dramatic, and accounts vary in detail. Historians still argue whether some reports were embellished by excited newspapers, but there's no doubt the storm was extraordinary. You picture Earth's magnetic field writhing under the impact. The CME's magnetic orientation was strongly southward, allowing efficient reconnection with Earth's northward field. Energy poured into the magnetosphere, driving intense currents in the ionosphere and along the ground. Magnetometers of the era, simple but effective, recorded wild swings. Here's the grounding fact. Modern estimates suggest the Carrington Event may have reached a geomagnetic storm intensity comparable to a DST index of around minus 850 nanoteslas, possibly even stronger. For comparison, the 1989 Quebec storm reached about minus 589 nanoteslas. Carrington was in another league. Now, let your mind fast forward to today. In 1859, the world ran on muscle, steam, and early electricity. Telegraph wires were the cutting edge. There were no satellites, no aviation networks, no global power grids stretching across continents. The technological web was thin. If a Carrington-level event struck now, the consequences could be far more disruptive. That's not alarmism. It's a straightforward extrapolation. Modern infrastructure is vastly more interconnected and electrically dependent. Studies commissioned by space weather agencies have modeled potential impacts. Some suggest that severe geomagnetic storms could damage high-voltage transformers, leading to prolonged regional blackouts. Others argue that grid operators have implemented safeguards, like improved grounding and monitoring, that would mitigate worst-case scenarios. Historians still argue whether contemporary society is resilient enough or quietly overconfident. There's also a fascinating fringe angle. Evidence from tree rings indicates that even more extreme solar particle events may have occurred long before 1859. In 2012, scientists reported a spike in carbon, 14 levels in tree rings dating to 774 to 775 AD, suggesting an intense burst of cosmic radiation. The leading hypothesis is an extreme solar event, possibly stronger than Carrington. If true, it means the sun has thrown even bigger tantrums than the one we remember. The debate continues. Some researchers propose alternative cosmic sources, like nearby supernovae, though solar origin remains the most widely accepted explanation. The uncertainty only adds to the sense that the sun's upper limits are not fully mapped. Back in 1859, though, people didn't speak of coronal mass ejections or magnetohydrodynamics. They saw glowing skies and malfunctioning wires. Some were frightened. Others were delighted. Telegraph operators, after recovering from mild shocks, likely had stories for the rest of their lives. You think your commute was rough? The sun tried to electrocute me. You let yourself stand in that Victorian night, under auroras so bright they cast shadows. There's awe there, and vulnerability, because the Carrington Event is more than a historical curiosity. It's a benchmark, a reminder etched into both scientific literature and popular imagination. Every time a powerful solar flare erupts now, comparisons surface. Is this another Carrington? Usually the answer is no, but the question itself shapes how scientists watch. Modern observatories constantly monitor solar active regions for Carrington-like signatures, rapid magnetic complexity, strong shear, massive sunspot groups. Spacecraft at the L1 point keep vigilant watch for incoming plasma clouds. The goal isn't to prevent a storm. You can't negotiate with a star, but to prepare. You feel the quiet tension in that preparation. The Carrington Event sits in collective memory, like a distant thunderclap. It tells you that the sun is capable of reaching beyond beautiful auroras and into technological disruption. And as solar cycle 25 climbs toward its peak, researchers aren't just counting sunspots. They're measuring the possibility, however small, that history could echo. Above you, the sun glows with the same serene brightness it had in 1859. No visible warning. No cosmic disclaimer. Just light. And the knowledge that once before, that light carried a storm strong enough to make telegraph wires spit fire. You leave the gaslit streets of 1859 behind and return to the present, where the world hums, not with telegraph clicks, but with fiber optics, GPS timing signals, and billions of quiet electronic pulses stitching continents together. If the Carrington Event were a lightning strike in a sparsely furnished room, today's civilization is that same room packed wall to wall with delicate glassware. You start by picturing the power grid. Vast generating stations feed electricity into high-voltage transmission lines that stretch hundreds of kilometers. These lines connect regions into synchronized networks, balancing supply and demand in real time. It's one of humanity's greatest engineering achievements. It's also, from a geomagnetic perspective, an enormous antenna. When a strong geomagnetic storm hits, fluctuations in Earth's magnetic field induce currents in long conductors at ground level. These geomagnetically induced currents, GICs, flow through transmission lines and into transformers. Transformers are designed for alternating current at specific frequencies. When quasi-direct currents from geomagnetic disturbances seep in, they can drive transformers into saturation, overheating internal components. This isn't speculation. During the March 1989 storm, protective relays tripped within seconds in Quebec, collapsing the grid. In 2003, during the so-called Halloween storms, several satellites malfunctioned and power systems in Sweden experienced outages. These are modern reminders that solar storms and infrastructure do, in fact, interact. Now imagine scaling that up. Today's grids are larger and more interconnected than they were in 1989. That interconnection improves efficiency, but can also allow disturbances to propagate. Historians still argue whether increased grid interdependence makes systems more resilient through redundancy or more vulnerable through cascading failures. The answer, like most things in engineering, is probably it depends. You shift your focus upward, beyond the atmosphere, to the invisible scaffolding of satellites. GPS alone underpins astonishing portions of modern life. It doesn't just guide your car. It synchronizes financial transactions, telecommunications networks, and even power grid timing. A nanosecond matters when markets trade at algorithmic speeds. Solar storms can degrade GPS accuracy by disturbing the ionosphere, introducing errors into signal propagation. During intense space weather events, positioning errors can increase significantly. Usually corrections and backups compensate, but the reliance is real. And then there are the satellites themselves. Communication satellites in geostationary orbit sit about 36,000 kilometers above Earth, parked relative to the surface. They endure radiation from the Van Allen belts and occasional solar particle events. A severe solar storm can increase charging on satellite surfaces, leading to electrostatic discharges, tiny lightning bolts across sensitive electronics. In 1994, a geomagnetic storm contributed to the failure of two Canadian communication satellites, Onyx E1 and E2, disrupting television and data services for hours. That was 3 decades ago. Since then, orbital real estate has become crowded. Thousands of satellites now circle Earth, with mega constellations providing global internet coverage. It's slightly surreal when you think about it. You stream a movie at night, and part of that data may have bounced off a satellite vulnerable to particles born in a sunspot you never saw. There's also aviation. Beyond radio communication disruptions, high-energy solar particle events can increase radiation exposure at cruising altitudes, especially on polar routes where Earth's magnetic shielding is weaker. Aviation authorities monitor space weather closely. During strong events, airlines may reroute flights to lower latitudes, not because passengers would glow in the dark, but to minimize cumulative radiation dose and maintain communication reliability. You pause and consider something subtler: undersea cables. Most internet traffic travels through fiber optic cables across ocean floors. The fibers themselves transmit light and are immune to geomagnetic currents. But the repeaters, electronic amplifiers spaced along the cables, are grounded systems that could, in theory, be affected by strong geomagnetic disturbances. Research in this area is ongoing. Historians still argue how vulnerable global internet infrastructure truly is to extreme solar storms, because we haven't yet experienced a Carrington-scale event in the fiber optic era. The modern world is a web of timing, electricity, and orbiting machines. In 1859, a solar storm made telegraph spark. Today, it could ripple through banking systems, satellite fleets, navigation networks, and supply chains. And yet, it's not all doom and cascading darkness. Engineers and grid operators are not unaware. Monitoring systems now track geomagnetic activity in real time. Some transformers are designed with better tolerance. Utilities conduct vulnerability assessments. Satellites include radiation-hardened components and safe modes that can be activated during storms. There's preparation layered into the system, like insulation around a wire. There's even an odd historical footnote. During the Cold War, certain early warning radar systems occasionally picked up disturbances linked not to enemy launches, but to solar activity. It added an extra layer of tension to already tense decades. Imagine almost mistaking the sun for a missile. That's the kind of misunderstanding you prefer to avoid. You feel the scale of dependency now. Your phone's map, the power charging it, the satellites guiding ships through fog, the timestamps on global transactions. So much of it is synchronized by signals traveling through layers of atmosphere shaped, subtly and sometimes dramatically, by solar behavior. Historians still argue whether society's increasing reliance on space-based assets has outpaced public awareness of space weather risk. Ask someone about hurricanes or earthquakes, and they likely have a mental model. Ask about geomagnetic storms, and you may get a blank stare or a sci-fi reference. But up in observatories and forecasting centers, there are no blank stares. There are dashboards of solar imagery, magnetometer readings, solar wind speeds, proton flux charts. The watching is constant now, because the stakes are woven into daily life. You look back toward the sun, still brilliant, still apparently calm. It doesn't know about stock markets or streaming services. It doesn't care about satellite constellations. It simply fuses hydrogen into helium, churns its magnetic fields, and occasionally sends storms outward. The difference is that now, More than at any other point in history, you've built a civilization that listens to those storms, sometimes the hard way. You lift your gaze again past the power lines and GPS signals, up into low Earth orbit, where thousands of satellites glide in silent arcs around the planet. They look serene from the ground, tiny, steady points of light slipping across twilight. But up close, they live in a far more dynamic environment than you might expect. Space is not empty. It's filled with plasma, radiation, and the ever-present outflow of charged particles from the sun known as the solar wind. During quiet solar conditions, satellites operate within predictable parameters. Engineers calculate atmospheric drag, radiation exposure, orbital decay. Everything is tidy, at least on paper. Then the sun flares. When solar activity increases, Earth's upper atmosphere heats up. Extreme ultraviolet radiation from flares in active regions deposits energy into the thermosphere, causing it to expand. And when the thermosphere expands, it increases drag on satellites in low Earth orbit, especially those a few hundred kilometers up. Here's the mainstream physics. Atmospheric density at orbital altitudes can increase significantly during geomagnetic storms. Even small changes in density translate into noticeable drag at orbital speeds of roughly 28,000 kilometers per hour. Satellites slow down, lose altitude, and require course corrections to maintain orbit. In February 2022, after a moderate geomagnetic storm, dozens of newly launched Starlink satellites failed to reach their intended orbits. Increased atmospheric drag caused them to re-enter and burn up. It wasn't a catastrophic loss in global terms, but was a clear example of solar activity affecting modern infrastructure in real time. Space weather claimed casualties, quietly and visibly, but undeniably. You imagine a satellite encountering a surge of charged particles. High-energy protons and electrons can penetrate shielding and accumulate on surfaces, building up electric charge. If the differential becomes large enough, it can discharge in a sudden arc, essentially a microscopic lightning strike across circuitry. Engineers call this surface charging or deep dielectric charging, depending on where it occurs. It sounds dramatic, but satellites are built with these risks in mind. Radiation-hardened electronics, shielding, fault-tolerant software, all designed to ride out solar tempests. Still, during major storms, operators may place spacecraft into safe mode, temporarily suspending non-essential functions until conditions stabilize. It's the orbital equivalent of closing the windows before a thunderstorm rolls through. Historians still argue whether the rapid commercialization of space has created uneven standards in radiation resilience. Government satellites often undergo rigorous hardening processes, but newer commercial ventures, especially small satellites built on tight budgets, may accept higher risk in exchange for lower cost. The debate isn't about negligence. It's about trade-offs in a rapidly evolving space economy. You drift higher toward geostationary orbit. Here, satellites remain fixed over one longitude, matching Earth's rotation. Many communication and weather satellites live here. During geomagnetic storms, the radiation belt surrounding Earth can become energized, injecting high-energy particles into regions where satellites reside. This can increase the likelihood of anomalies. A well-documented example occurred during the 2003 Halloween solar storms, when multiple satellites experienced operational issues. Japan's Adios 2 satellite was lost shortly after, though its failure involved a combination of factors. The timing underscored how vulnerable even sophisticated spacecraft can be during extreme space weather. And yet, satellites are not merely victims in this story. They are also sentinels. Spacecraft like NASA's ACE, Advanced Composition Explorer, and SCOVSIT at the L1 Lagrange point, about 1.5 million kilometers from Earth toward the Sun. From there, they monitor incoming solar wind and magnetic field conditions. They provide precious minutes of warning before CME's shock front reaches Earth. It's not much time, but in grid operations and satellite management, minutes matter. There's also a delightfully niche tidbit. During strong geomagnetic storms, increased atmospheric drag can actually help reduce space debris by nudging small fragments into lower orbits where they burn up faster. It's as if the sun occasionally tidies Earth's orbital clutter aggressively. Not exactly Marie Kondo, more like cosmic leaf blower. Still, the broader concern remains. With mega constellations deploying thousands of satellites, cumulative exposure to space weather becomes statistically significant. Even if each individual satellite has a low probability of failure during a storm, large numbers mean higher chances that some will glitch. You imagine mission control rooms scattered across the globe, California, French Guiana, India, Japan, engineers watching telemetry streams, battery voltage, temperature, orientation, radiation counters ticking quietly. When solar particle flux spikes, tension rises, commands are prepared, systems are checked, and above it all, the sun continues its magnetic ballet. There's a deeper scientific question woven into this vigilance. How well do we truly understand the coupling between solar activity and Earth's upper atmosphere? Models simulate thermospheric expansion, but density variations can still surprise forecasters. Historians still argue whether current atmospheric models fully capture the complex interplay between solar EUV radiation, geomagnetic heating, and chemical reactions in the upper layers. You sense how layered the system is. Sun to solar wind to magnetosphere, magnetosphere to thermosphere, thermosphere to satellites. A chain of cause and effect stretching across millions of kilometers. From your backyard, you see none of this. Just a faint satellite drifting across the night sky, steady and quiet. Maybe you wave at it. Maybe you don't notice it at all. But that tiny moving point is flying through an environment shaped by a star's temper. And the people who build it are watching that star with extraordinary attention. Because even small miscalculations, multiplied across thousands of machines, can ripple outward. You float there for a moment, suspended between sun and satellite, aware that the space age has tethered your daily life to conditions in the corona. And the corona, as you now know, is anything but calm. You drift now from satellites to something far more fragile. Human bodies in orbit. Picture the International Space Station, circling Earth every 90 minutes at an altitude of roughly 400 kilometers. Inside, astronauts float through modules filled with cables, laptops, and the faint hum of life support systems. From the cupola window, Earth rolls beneath them in luminous blues and whites. It feels peaceful, protected, and in many ways it is. Earth's magnetic field extends outward into space, forming a protective bubble that shields low Earth orbit from much of the solar wind's charged particles. The ISS sits within this magnetosphere, which deflects a large fraction of harmful radiation. That's a mainstream, well-established fact. Astronauts in low Earth orbit are significantly shielded compared to what they will experience in deep space. But significantly shielded does not mean invulnerable. During strong solar particle events, bursts of high-energy protons accelerated by solar flares or shock waves from coronal mass ejections, radiation levels in near-Earth space can increase. Most of the time, doses remain within safe operational limits. Still, space agencies monitor solar activity constantly. Radiation detectors aboard the ISS measure exposure in real time. If levels spike, astronauts can retreat to more shielded areas of the station, such as modules with thicker walls or water supplies that help absorb radiation. It's sometimes described as a storm shelter protocol. Not because lightning is cracking outside, but because invisible particles are streaming through space at near relativistic speeds. You imagine being up there during a major solar event. You wouldn't see anything unusual at first. No glowing warning clouds. Just a quiet alert from mission control. Elevated proton flux detected. Please move to the designated shelter area. You'd float calmly, maybe with a slight nervous joke. Guess the sun's having feelings again. And wait it out. Radiation in space isn't just about acute exposure. There's also cumulative dose. Astronauts already receive higher radiation levels than people on Earth, even during quiet solar conditions. NASA and other agencies track lifetime limits carefully. The balance is delicate, exploration versus exposure. Historians still argue whether the greatest radiation risk for future deep space missions, like journeys to Mars, will come from chronic galactic cosmic rays or from acute solar particle events. Galactic cosmic rays are high-energy particles from outside our solar system, harder to shield against. Solar particle events, though intense, are more episodic and potentially predictable. The debate influences spacecraft design, mission timing, and shielding strategies. Now think beyond low Earth orbit. The Artemis program aims to return humans to the moon and eventually establish a sustained presence. The moon has no global magnetic field, and only a tenuous exosphere. Astronauts on the lunar surface will be far more exposed to solar particle events. A strong solar storm during a moonwalk could deliver significant radiation doses if proper shelter isn't available. Engineers are already planning for this. Proposed lunar habitats may include regular shielding, using lunar soil piled over structures to absorb radiation. Some concepts even suggest burying habitats partially underground. It's a strange image, humans hiding from sunlight on the moon. There's also a quirky historical anecdote from the Apollo era. During Apollo 16 and 17, solar activity was relatively quiet. But scientists later realized that if a major solar particle event like the August 1972 storm had occurred while astronauts were en route to or on the moon, they could have received dangerously high radiation doses. The storm happened between Apollo missions, an unsettling near miss. Timing, it seems, has always been part of space travel's silent gamble. Back in low Earth orbit, the ISS sometimes passes through a region called the South Atlantic Anomaly, a dip in Earth's magnetic field strength over parts of South America and the South Atlantic Ocean. In this region, radiation levels are slightly higher because the inner Van Allen radiation belt dips closer to Earth's surface. Instruments may be powered down during passages to prevent glitches. It's a reminder that even Earth's protective shield has thin spots. You float alongside an astronaut as they exercise on a treadmill, tethered by elastic straps to simulate gravity. Outside, the sun blazes. It doesn't look hostile. It looks like home. But the station's hull is a carefully engineered barrier between human biology and a radiation environment that fluctuates with solar mood swings. Scientists watch the sun closely not just for infrastructure, but for people, as humanity prepares for longer missions. Months in lunar orbit, years on the journey to Mars. Accurate space weather forecasting becomes essential. A warning of an incoming solar particle event could mean the difference between minor exposure and serious health risk. Forecasting models now integrate solar observations, magnetic field measurements, and particle acceleration theories in an attempt to predict when and how strongly these events will occur. Historians still argue whether current predictive capabilities are sufficient for deep space exploration timelines. Some researchers believe we're close to reliable short-term forecasting. Others caution that particle acceleration processes near the sun remain too complex for confident prediction. You sense the vulnerability in it all. Satellites can be replaced. Transformers can be rebuilt. But human tissue is not so easily swapped out. And yet, astronauts continue to fly. Plans for lunar bases and Mars missions advance. The dream of becoming a multi-planetary species persists, quietly dependent on understanding the behavior of one very local star. You glance back toward the sun. It radiates the same warmth that nourishes crops and lights oceans. It also occasionally launches storms that ripple through magnetospheres and spacecraft hulls. Up there, in orbit, people trust that the scientists watching that star will see the next outburst coming. And down here, you begin to understand why that vigilance has never mattered more. You travel from sunspots to satellites to astronauts sheltering behind aluminum walls, and now you turn your attention back to the sun itself, specifically to one of its most baffling secrets. It begins with a simple, almost impolite question. Why is the sun's outer atmosphere hotter than its surface? On the surface, the photosphere, the temperature averages about 5,500 degrees Celsius. Move upward into corona, however, and temperatures soar past 1 million degrees Celsius. In some regions, they climb even higher. That's not a rounding error. That's a full-blown astrophysical paradox. Heat is supposed to flow outward from hot to cool. The core of the sun, where nuclear fusion occurs, reaches about 15 million degrees Celsius. Energy radiates outward, gradually cooling as it reaches the surface. Logically, you would expect temperatures to continue dropping as you move away from the energy source. Instead, the corona blazes at temperatures hundreds of times hotter than the visible surface below it. This is known as the coronal heating problem, and has puzzled scientists for decades. You imagine hovering just above the photosphere, watching granules of plasma rise and fall like glowing oatmeal bubbles. Beneath that surface, convection churns relentlessly. Magnetic field lines thread upward through this boiling layer, piercing into the corona. The key, most researchers agree, lies in magnetism. Two leading explanations dominate the discussion. The first involves wave heating. The sun's turbulent surface motions generate waves, specifically Alfvén waves, along magnetic field lines. These waves travel upward into corona, carrying energy. Somehow, that energy must dissipate as heat. Observations have confirmed the presence of such waves, and spacecraft have measured them propagating through the solar atmosphere. The debate centers on whether they carry enough energy and whether it can be efficiently converted into thermal motion. The second explanation focuses on nanoflares, a term that sounds adorable but refers to tiny magnetic reconnection events occurring constantly throughout the corona. Proposed by solar physicist Eugene Parker in the 1980s, the idea suggests that countless small reconnection events release bursts of energy too small to detect individually, but collectively sufficient to heat the corona to extreme temperatures. Historians still argue whether wave heating, nanoflares, or some combination of both dominates. The evidence supports elements of each mechanism. The sun, unhelpfully, may be using multiple methods at once. You picture magnetic field lines in the corona twisting and braiding like overenthusiastic headphone cords. When they become too stressed, they reconnect, snapping into new configurations and releasing energy. It's elegant and chaotic at the same time. This isn't just an academic puzzle. Coronal heating is intimately tied to solar wind acceleration, the steady stream of charged particles flowing outward from the sun in all directions. The solar wind fills the heliosphere, the vast bubble carved out by our star in interstellar space. Variations in the solar wind influence space weather conditions near Earth. NASA's Parker Solar Probe, launched in 2018, has been diving closer to the sun than any spacecraft before it. Skimming to the outer corona itself, it has already provided groundbreaking data, confirming that the solar wind is more structured and dynamic than previously thought. Measurements suggest that magnetic switchbacks, sudden reversals in magnetic field direction, may play a role in energy transfer. It's as if the solar wind occasionally does sharp U-turns for reasons we're still deciphering. There's also a quirky historical note. When scientists first measured the corona's high temperature in the early 20th century using spectroscopy, they initially thought they had discovered a new element, which they named coronium. It turned out not to be a new element at all, but highly ionized iron emitting light at unusual wavelengths due to extreme temperatures. Imagine thinking you've discovered a cosmic substance, only to realize it's just iron having an identity crisis at 1,000,000 degrees. The coronal heating problem remains one of astrophysics' most enduring mysteries, and solving it isn't merely about intellectual satisfaction. Understanding how energy moves through the sun's atmosphere improves models of solar eruptions, flares, and the solar wind, all of which affect Earth. You drift outward again, watching plasma loops arch high above sunspot regions. These loops glow in ultraviolet wavelengths, tracing magnetic highways. They shimmer and shift over hours and days. Somewhere within them, energy is being transferred, converted, amplified. Historians still argue whether our current instruments have sufficient spatial resolution to observe the smallest heating events directly. Some believe we're on the cusp of resolving nanoflares individually. Others suspect the true mechanism may involve plasma turbulence at scales even finer than we can currently measure. There's a certain humility in this. For all your satellites, grids, and missions, you still don't fully understand why the sun's outer atmosphere behaves the way it does. The star that sustains life on Earth guards fundamental secrets in plain sight. You imagine lying back beneath the night sky, feeling the residual warmth of a day powered by nuclear fusion. The same sun that grows crops and lights oceans also sustains a corona hotter than logic suggests. It humbles you. Scientists watch more closely than ever, not only because the sun can disrupt technology, but because it still surprises them at the most basic physical level. A nearby star, for 0.6 billion years old, still refuses to give up all its answers. And as new data streams in from probes daring to skim its atmosphere, you sense that you're living in an era where this ancient mystery might finally begin to yield. Or, in true cosmic fashion, become even more intriguing. You've hovered above the sun's surface, traced its magnetic loops, and puzzled over its superheated corona. Now, gently, you begin to descend, not into flame, but into theory. Because no spacecraft can dive into the sun's core, and yet scientists still claim to know what's happening down there. How? The answer is both elegant and slightly magical. They listen to it. This field is called helioseismology, and it works on a principle similar to how seismologists study Earth's interior using earthquake waves. The sun, though made of plasma rather than rock, vibrates constantly. Turbulent convection beneath the surface generates pressure waves, sound waves, that bounce around inside the solar interior. These waves cause the surface to oscillate ever so slightly. You wouldn't see it with your eyes. The surface rises and falls by only a few kilometers over a sphere nearly 1.4 million kilometers wide. But instruments can detect these subtle motions as Doppler shifts, tiny changes in the wavelength of light emitted from the surface. It's a mainstream scientific triumph. By measuring these oscillations, researchers can infer temperature, density, and motion deep within the sun. They can map regions they will never physically touch. Imagine placing your ear against a massive, glowing sphere and hearing a hum. The sun's oscillations have characteristic frequencies, millions of resonant modes overlapping in a complex symphony. Each mode penetrates to a different depth. By analyzing them, scientists reconstruct the sun's inner structure, and what they've learned is astonishing. Beneath the visible surface lies the convection zone, extending down about 200,000 kilometers. Here, hot plasma rises and cool plasma sinks in vast rolling currents. Below that sits the radiative zone, where energy moves outward primarily through radiation rather than convection. And at the very center lies the core, where hydrogen nuclei fuse into helium, releasing energy according to Einstein's famous equation, E equals mc squared. That fusion process has been confirmed not just through theory, but through the detection of solar neutrinos, tiny, nearly massless particles produced during nuclear reactions in the core. For decades, scientists detected fewer neutrinos than predicted, leading to the so-called solar neutrino problem. Historians still argue whether this was one of the most satisfying scientific puzzles of the 20th century. The mystery was eventually resolved when physicists discovered that neutrinos change flavors as they travel, meaning detectors were only seeing part of the total flux. The sun wasn't malfunctioning. Our understanding was, you imagine neutrinos streaming through your body right now, trillions per second, passing almost entirely unnoticed. They left the sun's core mere seconds ago and traveled straight through space and matter alike. They are direct messengers from the heart of a star. Helioseismology has also revealed something crucial to understanding the solar cycle. Differential rotation extends deep into the convection zone. The equator rotates faster than the poles, and at the boundary between the radiative and convection zones lies a thin shear layer called the tachocline. This region is believed to play a central role in generating the sun's magnetic dynamo. The solar dynamo is the engine behind the 11-year cycle, the process that twists plasma motion into magnetic fields, amplifies them, and eventually flips the sun's polarity. Yet despite decades of modeling, the exact details remain elusive. Computer simulations attempt to replicate the dynamo, but the sun operates at scales and conditions that push computational limits. Historians still argue whether current dynamo models capture the full complexity of plasma turbulence in the tachocline. Some suggest missing ingredients. Perhaps subtle feedback loops between flows and fields are yet to be discovered. The sun, once again, keeps a layer of mystery beneath its blazing exterior. There's a quirky detail here, too. The sun doesn't just ring like a bell. It rings in many tones simultaneously. At any given time, thousands of oscillation modes ripple across its surface. It's less a single note and more a constantly shifting chord. If you could convert those oscillations into audible sound, you'd hear something like a deep, resonant hum, lower than human hearing, but mathematically translatable. Scientists have done exactly that, speeding up the frequencies into the audible range. The result is oddly soothing. The sun, it turns out, has vibes. You float there in imagination, descending through layers you can't physically enter. In the core, temperatures reach about 15 million degrees Celsius. Pressure is immense, hundreds of billions of times Earth's atmospheric pressure. Hydrogen nuclei overcome their mutual electric repulsion and fuse, converting mass into energy. Every second, the sun converts about 600 million tons of hydrogen into helium. About 4 million tons of mass become pure energy each second. And yet, despite that staggering output, the sun is considered an average star. Not the largest, not the brightest, just steady. That steadiness is part why scientists care so deeply about understanding its interior. Small changes in internal flows can influence magnetic field generation. Magnetic fields drive sunspots. Sunspots spawn flares and CMEs. CMEs disturb Earth. It's a chain that begins in a place you will never see directly. Helioseismology has even detected subtle variations in internal rotation rates over the solar cycle. Bands of slightly faster and slower rotation migrate with the cycle, like torsional oscillations rippling through convection zone. These patterns provide clues about how magnetic fields build and reverse. And still, questions remain. Historians still argue whether there are deeper, longer-term cycles hidden beneath the familiar 11-year rhythm. Cycles spanning centuries that modulate solar intensity in ways we are only beginning to glimpse through isotopic records. You slowly rise back toward the surface in your mind. Carry with you the knowledge that the sun is not a simple ball of fire. It is layered, dynamic, resonant. Scientists are watching more closely than ever, not only because of what erupts from the surface, but because of what stirs far below it. They are listening to the hum of a fusion engine 93 million miles away, decoding vibrations to anticipate magnetic moods. And as you return to that glowing photosphere, you feel a quiet awe. The star above you is singing, and for the first time in history, you are beginning to understand its tune. Now you leave the safety of theory and instruments anchored to Earth's orbit, and you hitch a ride on something far more daring. It's 2018. A rocket lifts off from Cape Canaveral, carrying a spacecraft no larger than a small car. Its destination is not Mars, not Jupiter, but the sun itself. This is NASA's Parker Solar Probe, named after Eugene Parker, the same physicist who proposed the existence of the solar wind in 1958, a theory initially met with skepticism. Historians still argue whether Parker's early reception says more about scientific caution or about how uncomfortable bold ideas can be. Either way, He lived to see a spacecraft bear his name. Not a bad career arc. You feel the probe accelerate, looping around the sun in increasingly tight orbits. It uses repeated gravity assists from Venus to shrink its path, each flyby stealing a bit of orbital energy. With every pass, it dives closer. Eventually, Parker Solar Probe schemes within about 6 million kilometers of the sun's surface, closer than any spacecraft in history. At that distance, sunlight is roughly 500 times more intense than what you feel on Earth. The probe is protected by a carbon composite heat shield about 11 centimeters thick, designed to withstand temperatures approaching 1,400 degrees Celsius. Behind that shield, instruments remain at near room temperature. It's like holding an ice cube behind a blast furnace door and somehow keeping it solid. You imagine standing on the probe, again hypothetically, because you'd last about a fraction of a second, watching the corona swirl around you. For the first time, a human-made object is flying through the sun's outer atmosphere. And what it finds is surprising. Before Parker, scientists pictured the solar wind as a relatively smooth outflow of charged particles. But as the probe plunged into corona, it detected sudden, sharp reversals in the magnetic field. Structures now called switchbacks. These are zigzagging kinks in magnetic field lines, where the direction flips abruptly and then flips back. The mainstream data is clear. Switchbacks are far more common near the sun than previously thought. They may play a significant role in accelerating the solar wind. But how exactly they form remains under investigation. Are they generated by processes at the solar surface? Or do they emerge from turbulence higher up? Historians still argue which mechanism dominates. The probe also crossed a critical boundary known as the Alphane critical surface, the point where the solar wind transitions from being magnetically dominated to kinetically dominated. In simpler terms, it's where the solar wind stops feeling anchored to the sun's magnetic field and begins flowing freely into interplanetary space. Crossing that boundary was a milestone decades in the making. You picture the moment. Instruments humming, data streaming back across millions of kilometers, scientists on Earth watching graphs update in near real time. The sun is no longer just observed from afar. It is being sampled directly. There's something almost poetic about it. For millennia, humans worshipped the sun, feared it, depended on it. Now, you built a machine that dares to touch its atmosphere. Parker has also measured unexpectedly high-energy particles close to the sun, shedding light on how solar energetic particle events accelerate. Understanding these processes is essential for predicting radiation hazards for astronauts and satellites. The closer you measure the source, the better your models become. And then there's the speed. At its closest approach, Parker Solar Probe travels at over 600,000 kilometers per hour, making it the fastest human-made object in history. Fast enough to go from New York to Tokyo in under a minute. Not that it would stop for layovers. The mission is rewriting textbooks in subtle ways. Data suggests that the corona is structured by fine magnetic strands, constantly reconnecting and reshaping. Plasma behaves less like a smooth fluid and more like a restless, braided tapestry of fields and particles. Historians still argue whether the full implications of Parker's findings will require revision of long-standing solar wind acceleration models. Some researchers believe we're witnessing a paradigm shift. Others think it's an incremental refinement. Science, as always, leans toward patience. There's a delightful irony in all of this. To understand space-weathered Earth, you had to send a probe nearly into the sun. It's like diagnosing a distant storm by flying straight into the hurricane's eye. And yet, despite the daring, Parker Solar Probe is not reckless. Its trajectory is meticulously calculated. Its instruments are shielded and redundant. It doesn't hover. It swoops in and out, gathering data in bursts during each perihelion pass. Every orbit brings it closer, deeper, hotter. You float beside it as it rounds the sun, shield facing forward, instruments peeking out from behind detective edges. The corona glows in ultraviolet light, threaded with magnetic loops. Plasma flows past in gusts and streams. This is why scientists are watching more closely than ever, because now, for the first time, they are not merely spectators. They are participants in a direct encounter. The sun is no longer just a distant sphere in a telescope. It is an environment being sampled, measured, mapped from within. And as Parker continues its daring dives, each pass adds another layer of understanding to the story you've been tracing. From sunspots to storms to satellites and astronauts, you begin to sense that the age of passive observation is over. Now, you are reaching into the corona itself, asking the star to explain how it works. And slowly, in data packets traveling across space, it is answering. And just as Parker Solar Probe dares to skim the sun's atmosphere, another spacecraft takes a different path. Less of a plunge, more of a strategic sidestep. You follow the European Space Agency's solar orbiter, launched in 2020, gliding inward through the inner solar system. Unlike Parker, which prioritizes proximity, Solar Orbiter balances closeness with perspective. It carries high-resolution cameras alongside in-situ instruments, meaning it both tastes the solar wind directly and photographs the sun in extraordinary detail. But its most ambitious goal isn't just sharper images. It's latitude from Earth. And even from most spacecraft, you view the sun from roughly the same flat plane, the ecliptic. You see the equator head-on, like staring at a spinning coin from its edge. The poles remain foreshortened, mysterious. And yet, the poles are crucial. They're where the sun's global magnetic field reverses during each solar cycle. Solar Orbiter is gradually tilting its orbit out of that flat plane using gravity assist from Venus. Over time, it will climb to higher inclinations, offering humanity its first clear views of the sun's polar regions. You imagine rising above the solar equator, looking down at the poles directly for the first time. Instead of a blur at the limb, you see magnetic structures in detail. Open field lines streaming into space, polar plumes shimmering in ultraviolet light. Here's the mainstream fact anchoring the excitement. The sun's magnetic cycle, its 11-year rhythm, is driven by processes that likely depend heavily on polar magnetic fields. At solar minimum, the poles host relatively simple magnetic configurations. As the cycle progresses toward maximum, magnetic complexity increases, and eventually the polar fields weaken, flip, and rebuild with opposite polarity. Yet despite decades of observation, scientists still lack continuous, high-resolution data of polar magnetism. Historians still argue whether limitations in polar data have constrained the accuracy of solar cycle predictions. Some researchers believe better polar measurements could dramatically improve forecasting models. Others caution that the solar dynamo may be too inherently chaotic for precise long-term prediction. Solar Orbiter has already delivered stunning imagery. In 2022, it captured the highest resolution full-disk images of the sun ever taken. The surface appears as a mosaic of tiny bright cells, each one a convective granule roughly the size of France. It's humbling to realize that what once looked smooth and featureless is actually textured like a living surface. There's also a wonderfully odd discovery. Solar Orbiter has observed tiny eruptions dubbed campfires. These are small, short-lived brightenings scattered across the corona. They're much smaller than full solar flares, but they may be signatures of the nanoflares proposed to explain coronal heating. Remember those from earlier? The adorable name, the million-degree implications. Are campfires the smoking guns of coronal heating? Possibly. Historians still argue whether these events release enough energy collectively to account for the corona's extreme temperature. But their existence strengthens the case that small-scale magnetic reconnection is happening everywhere, all the time. You float beside Solar Orbiter as it angles upward, gradually increasing its inclination. Each orbit reshapes your view of the sun. The poles, once hidden, begin to open like pages in a long sealed book. The poles also play a central role in shaping the heliosphere, the vast bubble carved by the solar wind into interstellar space. During solar minimum, fast solar wind streams emerge from polar coronal holes, sweeping outward at high speeds. During solar maximum, this orderly pattern becomes chaotic. Understanding polar dynamics means understanding how the entire heliosphere breathes. And that matters. The heliosphere is your first line of defense against galactic cosmic rays. Its size and structure influence how much high-energy radiation penetrates into the inner solar system. Changes in solar activity ripple outward to the very edge of the sun's domain. There's a subtle poetry in this. By studying the poles of a star, you refine your understanding of radiation levels millions of kilometers away. Solar Orbiter also collaborates indirectly with Parker Solar Probe. When their positions align just right, one can sample solar wind that the other has imaged at its source. It's like watching smoke rise from a chimney and then flying through the plume to test its composition. Coordinated solar science, because even spacecraft need teamwork. You sense how this is different from earlier eras. Galileo sketched sunspots. 19th century astronomers counted cycles. Now, robotic emissaries weave intricate trajectories around Venus, tilting and diving to reveal hidden angles. Scientists are watching more closely than ever because they finally can. And yet, even with new data pouring in, the sun resists being fully predictable. Magnetic fields emerge in patterns that surprise forecasters. Cycle 25 rose faster than many models anticipated. Polar field strengths fluctuate in ways that challenge neat equations. Historians still argue whether the solar cycle will ever be forecast with the same confidence as seasonal weather patterns on Earth. The sun is simpler in composition, mostly hydrogen and helium, but far grander in scale and magnetic complexity. You drift slowly away from solar orbiter, watching it continue its patient climb toward higher latitudes. The poles gleam faintly in ultraviolet light, their magnetism quietly orchestrating the next reversal. The story has grown quieter now, not fewer questions, but deeper ones. You've seen storms and flares and satellites trembling under invisible currents. Now you're witnessing something subtler, the slow, deliberate turning of a star's magnetic heart. And as your journey eases into a softer rhythm, you feel the vastness of time wrapped around this cycle. 11 years at a time, over billions of years. The sun will flip its poles again. It always does. You inhale gently, imagining that distant reversal, that steady cosmic pulse continuing long after headlines fade. Out there, above the equator and beyond the poles, a star turns, reverses, renews. And you, small and luminous with borrowed starlight, drift in its quiet glow. You linger in that soft glow of polar light, watching magnetic fields slowly reorganize themselves. And now your attention shifts from observing the sun to try and predict it. Because watching is one thing, forecasting is another. Down on Earth, in quietly humming operation centers, scientists track solar data the way meteorologists track hurricanes. Screens display real-time images from solar telescopes, X-ray flux graphs, proton counts, magnetometer readings. There are color-coded alerts and probability charts. It looks almost ordinary until you remember that all of it concerns a star 93 million miles away. Space weather forecasting is a relatively young science. The term itself only gained widespread use in the late 20th century. Before satellites and global grids, there wasn't much practical reason to predict solar storms beyond scientific curiosity. Now, it's an operational necessity. The mainstream framework works like this. Solar observatories detect active regions, complex sunspot groups with twisted magnetic fields. Analysts assess their configuration using classification systems, such as the Mount Wilson Magnetic Classification. If a region shows strong magnetic shear and mixed polarities, particularly a beta-gamma-delta configuration, it has a higher probability of producing major flares. Probability is the key word. Even today, flare forecasting remains probabilistic, not deterministic. Scientists might say there's a 30% chance of an M-class flare in the next 24 hours. That's useful, but it's not the same as predicting a thunderstorm at 3:42 p.m. When a flare does occur, satellites such as GOES geostationary operational environmental satellites detect the X-ray spike within seconds. Automated alerts go out to airlines, satellite operators, power grid managers. If a coronal mass ejection is launched, coronagraphs, telescopes that block out the bright solar disk, track the expanding cloud of plasma. You imagine watching that cloud balloon outward on a screen, like ink spreading in water. Analysts estimate its speed and trajectory. Is it Earth-directed? How fast is it traveling? A fast CME can reach Earth in as little as 15 to 18 hours. Slower ones may take 2 or 3 days. But here's the challenge. Predicting impact severity depends not just on whether the CME hits Earth, but on the orientation of its magnetic field. If the CME's embedded magnetic field points southward relative to Earth's field, geomagnetic coupling is stronger. Unfortunately, that orientation is often unknown until the CME is almost upon us. That's why spacecraft position at the L1 Lagrange point are so crucial. They sample the solar wind about 1.5 million kilometers upstream from Earth, giving forecasters roughly 30 to 60 minutes of warning before impact. It's not much time, but it's enough to issue alerts and prepare systems. Historians still argue whether placing additional monitoring spacecraft at different vantage points, such as the L5 Lagrange point, which will provide a side view of incoming CMEs, would significantly improve forecast accuracy. Some agencies are actively planning such missions. The idea is simple: better angles, better predictions. There's a slightly charming comparison often made in the field. Space weather forecasting today is roughly where terrestrial weather forecasting was in the mid-20th century. Basic models exist. Observations are improving, but precision remains limited. You can predict the season of storms more reliably than the exact strike of lightning. And yet, progress is steady. Machine learning models now analyze decades of solar data, searching for subtle patterns that might precede eruptions. High-resolution magnetograms map surface fields in exquisite detail. Global networks of ground-based magnetometers track geomagnetic disturbances in real time. There's also international coordination. Organizations like NOAA Space Weather Prediction Center in the United States, the European Space Agency Space Weather Service Network, and similar agencies in Japan, India, and elsewhere share data continuously. The sun, after all, does not respect national borders. A geomagnetic storm hitting one hemisphere can ripple across a globe. You picture a scenario: a large sunspot group rotates into view. Magnetic complexity increases. Forecast probability rises. An X-class flare erupts, followed by a halo CME, meaning it appears to expand outward in all directions. A strong sign it's heading toward or away from Earth. Analysts run models. Estimated arrival, 36 hours. Grid operators receive notifications. Satellite controllers prepare safe modes. Airlines consider rerouting polar flights. It's a choreography of quiet readiness. Historians still argue whether public awareness of space weather should be higher. Some suggest routine alerts would cause unnecessary alarm. Others believe broader understanding would foster resilience and appreciation for the sun's influence. The truth is that most solar storms pass with little disruption. Auroras flare. Social media fills with glowing skies, and life continues uninterrupted. The system works because people are watching. You feel a subtle reassurance in that. The sun may be unpredictable in detail, but it is not ignored, and forecasting continues to improve. Each solar cycle provides new data. Each mission refines models. Each storm becomes a case study. There's a quiet heroism in it. Scientists staring at ultraviolet images try to read magnetic hieroglyphs written in plasma. You tilt your head back toward that brilliant disk in the sky. It looks the same as it did this morning, the same as it did centuries ago. But now you know that behind the scenes, probabilities are being calculated. Alerts stand ready. Forecast maps update hourly. The watching has evolved into anticipation. And while the sun will always retain an element of surprise, you are no longer entirely at its mercy. You are learning its rhythms. Slowly, patiently, one flare at a time. You've watched scientists scan magnetograms and coronagraph images, calculating probabilities like cosmic meteorologists. Now you step into a newer layer of the story, one that hums not with plasma, but with processors. Artificial intelligence has entered the solar conversation, not in a dramatic, robot staring at the sun way, but quietly, through pattern recognition. Modern solar observatories generate staggering amounts of data. NASA's Solar Dynamics Observatory alone captures high-resolution images of the sun every few seconds across multiple wavelengths. That's terabytes of data per day. No human team, no matter how caffeinated, can manually inspect every frame. So you teach machines to look. Machine learning algorithms are trained on historical datasets, images of active regions, records of which sunspot groups produce flares, measurements of magnetic complexity. The system learns correlations, subtle spatial patterns in magnetic field distributions that tend to precede eruptions. The mainstream reality is this: AI-based models have begun to match or slightly outperform traditional statistical flare forecasting methods in certain tests. They're particularly good at identifying complex, high-risk active regions. But they are not oracles. They don't understand the sun. They recognize patterns in data. You imagine feeding decades of solar imagery into a neural network. It adjusts internal weights, searching for features invisible to naked eye, tiny asymmetries, gradients, configurations that historically led to flares. When a new active region rotates into view, the algorithm assigns a probability score. It's not magic. It's mathematics at scale. Historians still argue whether machine learning will fundamentally transform space weather forecasting or simply refine existing tools. Some researchers are enthusiastic, believing AI can uncover nonlinear relationships too complex for traditional models. Others caution that AI systems can be opaque, producing predictions without clear physical explanations. In solar physics, understanding the why matters just as much as predicting the when. There's also the issue of rare events. Extreme solar storms, Carrington level or stronger, are statistically scarce in modern datasets. Machine learning thrives on large numbers of examples. Training an algorithm to predict something that rarely happens is inherently difficult. It's like teaching a system to anticipate a once-in-a-century storm using only a few historical snapshots. Still, progress is undeniable. AI is also being used to track coronal mass ejections automatically in coronagraph imagery. Instead of a human analyst manually outlining the expanding cloud, algorithms detect edges, estimate speed, and project trajectories in near real time. This speeds up forecasting and reduces subjective interpretation. You picture a control room where software flags a CME within seconds of its appearance, calculating its velocity and probable arrival time before a human even finishes a sip of coffee. Efficient, tireless, slightly intimidating. Beyond forecasting, AI helps reconstruct the sun's magnetic field in 3 dimensions. By combining surface magnetograms with physical models, machine learning assists in extrapolating coronal field structures, those invisible lines that store energy before flares erupt. There's a quirky irony here. To understand a 4.6 billion year old fusion reactor, you deploy algorithms developed in the last decade. Ancient plasma meets modern code, and yet AI doesn't replace physics. It complements it. Solar physicists still build magnetohydrodynamic simulations that attempt to replicate plasma behavior from first principles. These simulations require enormous computational power. AI sometimes steps in to approximate certain calculations more efficiently, acting as a shortcut through otherwise intractable equations. Historians still argue whether reliance on data-driven models could risk overlooking new physical mechanisms. If an AI is trained only on past behavior, how will it respond to something truly unprecedented? The sun, after all, has existed far longer than your datasets. There's also a broader philosophical question. Are you predicting the sun or predicting your measurements of it? Instruments evolve. Resolution improves. Calibration changes. AI systems must adapt to shifting data landscapes. Still, the collaboration between human insight and machine efficiency is accelerating discovery. When Solar Orbiter detects tiny campfires flickering across the corona, algorithms help catalog and analyze thousands of them. When Parker Solar Probe transmits streams of particle data, machine learning tools sift through fluctuations, identifying patterns that might otherwise be buried in noise. You imagine the sun as a vast, complex signal, and AI as a new kind of stethoscope, amplifying faint irregularities. Meanwhile, back on Earth, predictive dashboards update automatically. Probability curves adjust in real time as fresh data flows in. Alerts propagate through digital networks faster than any telegraph spark in 1859. There's a subtle comfort in this technological vigilance. Not because AI makes you invincible, but because it expands your awareness. You tilt your face toward the sky again. The sun remains as brilliant and inscrutable as ever. But now, somewhere in a data center, servers hum softly, analyzing its light pixel by pixel. Historians still argue whether future breakthroughs in solar forecasting will come from deeper physical theory or from increasingly sophisticated data analysis. Perhaps both. Perhaps the most powerful insights will emerge where physics and pattern recognition meet. For now, the watching has become smarter. Not perfect, not prophetic, but sharper. And as Solar Cycle 25 continues its climb, algorithms and astronomers alike keep their digital eyes fixed on that restless star, learning its habits one dataset at a time. You've traced magnetic fields, listened to oscillations, followed daring spacecraft, and now you arrive at a question that tends to spark raised eyebrows at dinner parties. Is the sun affecting Earth's climate right now? It's a delicate topic. The sun is, undeniably, the primary source of energy for Earth's climate system. Without it, your planet would be a frozen rock drifting in darkness. That's not controversial. That's thermodynamics. But when it comes to modern climate change, the role of solar variability becomes more nuanced. Let's begin with the mainstream science. The total solar irradiance, the amount of solar energy reaching the top of Earth's atmosphere, does vary slightly over the 11-year solar cycle. Measurements from satellites since the late 1970s show that this variation is about 0.1%. That's real, measurable, and linked directly to sunspot and faculae activity. During solar maximum, the sun actually emits slightly more total energy, despite the presence of dark sunspots, because bright magnetic regions called faculae more than compensate. However, that 0.1% fluctuation is relatively small compared to the radiative forcing associated with increased greenhouse gases over the past century. The overwhelming consensus in climate science is that recent global warming is driven primarily by human activities, not by changes in solar output. That said, the sun's variability is not irrelevant. You imagine the Maunder minimum again, that prolonged lull in sunspot activity between about 1645 and 1715. It coincided with cooler conditions in parts of Europe during the Little Ice Age. Frozen rivers, harsh winters, frost fairs on the Thames. Historians still argue whether reduced solar activity played a significant causal role or whether volcanic eruptions and internal climate variability were more dominant. Most likely, multiple factors interacted. There's also research into how ultraviolet variations over the solar cycle influence the stratosphere. While total irradiance changes are small, UV radiation can vary more significantly, affecting ozone chemistry and atmospheric circulation patterns. These subtle top-down influences may modulate regional climate patterns, even if they don't drive long-term global trends. It's complex, and complexity invites debate. Historians still argue whether long-term solar cycles beyond the familiar 11-year rhythm, such as potential centennial-scale variations, have had measurable climatic impacts in the past. Proxy records from tree rings and ice cores reveal fluctuations in isotopes like carbon-14 and beryllium-10, which are influenced by solar magnetic activity. These records suggest periods of higher and lower solar activity stretching back thousands of years. But translating those variations into precise temperature effects is challenging. Earth's climate system is not a simple thermostat. It's an intricate interplay of atmosphere, oceans, ice, land, and biosphere, all interacting across multiple timescales. You lie back in imagination under a bright midday sun day. It feels constant, reliable, yet over decades and centuries, its magnetic behavior subtly shifts. Not dramatically enough to explain modern warming trends, but enough to leave fingerprints in the geological record. There's also a fringe but persistent idea that cosmic rays, modulated by solar activity, influence cloud formation and thus climate. The hypothesis suggests that during periods of low solar activity, more galactic cosmic rays reach Earth, potentially enhancing cloud nucleation and increasing cloud cover, which could cool the planet. Experiments, including those at CERN's Cloud Project, have investigated aspects of this mechanism. So far, evidence indicates that while cosmic rays may contribute to aerosol formation under certain conditions, they are unlikely to be a dominant driver of recent climate change. Historians still argue how significant the effect might be under specific atmospheric scenarios, but it does not overturn the broader consensus. The reason scientists watch the sun so closely in climate studies is not to assign blame, but to refine understanding. Climate models incorporate solar irradiance data to ensure accurate attribution of observed temperature changes. If you want to isolate human influences, you must first account for natural ones. It's a bit like balancing a budget. You need to know all income sources before assessing new expenses. And here's something quietly reassuring. Because satellites now monitor solar output with high precision, you can say with confidence that the sun's energy has not increased in a way that explains recent warming. In fact, the most recent solar cycle was relatively weak compared to some earlier ones. That doesn't make the sun unimportant. It makes it measurable. You feel the subtle distinction settling in. The sun drives seasons. It fuels photosynthesis. It shapes atmospheric circulation. But its recent variations are too small to account for the magnitude of modern climate change. Still, scientists continue to monitor irradiance, UV flux, magnetic modulation of cosmic rays, because the more precisely you understand natural variability, the better you can model the future. Historians still argue whether a future grand solar minimum could slightly offset warming trends temporarily. Some models suggest it might provide a small cooling influence, but not enough to counteract greenhouse gas forcing significantly. It would be a gentle nudge, not a reset button. You look up at the sun again, feeling its warmth on your skin. It is constant on human timescales, variable on decadal ones, evolving on billion-year arcs. The story here is not one of blame, but of calibration. Scientists watch the sun more closely than ever because it is the baseline, the reference point, the original energy input to Earth's climate engine. To understand change, you must first understand the star that started it all. And so, while debates continue in journals and conferences, instruments keep measuring, satellites keep recording, data keeps accumulating. The sun shines, and you keep learning exactly how and how much it shapes the world beneath it. You watch the sun from orbit and from deep space, trace its influence on climate and satellites, and now you step into a place far less cosmic but equally dramatic, a power grid control room. The lighting is soft, the walls lined with screens. Operators monitor voltage levels, frequency stability. Power flows across transmission lines stretching hundreds of kilometers. It looks calm. It usually is. But on certain days, when solar alerts start arriving, that calm sharpens into focus. When a coronal mass ejection is predicted to impact Earth, space weather centers issue geomagnetic storm watches. These are categorized on a G scale from G1 minor to G5 extreme. A G5 storm is rare, but not theoretical. The 1859 Carrington Event would likely rank at or beyond that scale if it occurred today. Here's the mainstream engineering reality. Geomagnetic storms induce electric fields at Earth's surface. Those fields drive geomagnetically induced currents, GICs, through long conductive structures, such as high-voltage transmission lines. The longer the line and the higher the latitude, the greater the potential vulnerability. You imagine those currents flowing silently along steel and copper, entering transformers at substations. Large power transformers are critical components, custom-built, often weighing hundreds of tons. They're not sitting on warehouse shelves waiting for overnight shipping. If one is severely damaged, replacement can take months. After the 1989 Quebec blackout, utilities worldwide began studying GIC vulnerability more seriously. Monitoring systems were installed to measure geomagnetically induced currents directly. Transformer designs were evaluated. Operational procedures were updated. Now, when a significant geomagnetic storm is forecast, grid operators can take precautionary steps. They may adjust power flows to reduce stress on certain transformers. They might temporarily remove vulnerable equipment from service. They increase situational awareness. It's not dramatic from the outside, but inside the control room, it's a coordinated dance. Historians still argue whether global power infrastructure is uniformly prepared. High-latitude regions like Canada and Scandinavia tend to be more vulnerable due to stronger geomagnetic effects near the poles. Some countries have invested heavily in monitoring and mitigation. Others are still developing strategies. There's also the complexity of interconnected grids. In many regions, power systems are linked across state or national boundaries. That interconnection enhances reliability under normal conditions. If one area has excess generation, it can support another. But during disturbances, tightly coupled systems can also transmit stress. Cascading failures are rare, but they're studied carefully. You picture a strong CME striking Earth. Auroras bloom. Magnetometers spike. In control rooms, alerts sound, not sirens, just digital notifications. Operators watch reactive power levels. They track harmonics that might indicate transformer saturation. Protective relays stand ready. There's a peculiar irony. The more advanced your electrical infrastructure becomes, the more it resembles a sensitive instrument tuned to stability. And the sun, occasionally, plucks at that instrument. But it's not just power grids. Pipelines can also experience geomagnetically induced currents, which accelerate corrosion in certain conditions. Railway signaling systems have, in rare instances, been affected by geomagnetic disturbances. Even precision drilling operations that rely on magnetic references can experience subtle interference. Historians still argue whether extreme solar storm risk should be classified alongside natural disasters like earthquakes and hurricanes in national resilience planning. Some countries have begun incorporating space weather scenarios into emergency preparedness exercises. Others treat it as a low-probability, high-impact event, acknowledged, but not always prioritized. There's also encouraging progress. International standards organizations have developed guidelines for assessing transformer vulnerability. Research institutions model ground conductivity variations to understand where induced electric fields might be strongest. The geology beneath your feet, rock type, soil conductivity, actually influences how geomagnetic storms manifest locally. It's almost poetic. Ancient bedrock shapes modern electrical risk. You stand in that imagined control room as data streams in. A storm is underway. Operators speak calmly. Adjustments are made. The grid flexes, but holds. Most geomagnetic storms pass without major incident. That's partly because they're moderate. It's also because people are paying attention. And attention has grown sharper in recent years. Governments have issued space weather strategies. Agencies coordinate simulations of extreme events. Utilities share data across borders. Historians still argue whether the memory of the Carrington Event looms too large or not large enough in policy discussions. Is it an outlier that skews perception, or a warning insufficiently heeded? You glance back toward the sun in your mind. It doesn't know about substations or transformer cores. It simply releases energy according to the physics of plasma and magnetism. But down here, beneath that bright disk, engineers translate solar forecasts into operational decisions. They reduce load on vulnerable lines. They check backup systems. They prepare just in case. The watching is extended beyond observatories into infrastructure. It's no longer only about understanding a star. It's about living responsibly under one. And as the solar cycle climbs towards peak, those quiet rooms with glowing screens become part of the sun story too. Human nodes in a network shaped by distant magnetism. You feel a quiet confidence settle in. Not immunity, not invincibility, just readiness. The sun will do what it's always done. And you, increasingly, are learning how to adapt. You've seen how grids brace themselves and satellites slip into safe mode, but now you step into a question that makes even seasoned solar physicists pause. Could the sun produce something far bigger than anything in modern memory? Not just another Carrington-level storm. A superflare. The term sounds dramatic, like something from a comic book, but it has a legitimate astrophysical basis. Astronomers studying distant sun-like stars have observed flares thousands of times more energetic than the largest solar flares ever recorded on our sun. These are called superflares, and they release energies on the order of 10 superscript 3 to 10 superscript 3 ergs, orders of magnitude beyond typical X-class solar flares. The unsettling part? Some of those stars look remarkably similar to the sun. You imagine scanning distant solar analogs with space telescopes like Kepler. Instead of subtle brightness variations, you see sudden enormous spikes. Stellar outbursts so powerful, they briefly increase the star's total brightness by a noticeable fraction. It's not subtle. The mainstream question is simple. Could our sun do that? Evidence suggests that while the sun is capable of large flares, true superflares are likely rare for stars of its age, rotation rate, and magnetic activity level. The sun rotates relatively slowly, about once every 27 days at the equator, and stellar rotation is strongly linked to magnetic dynamo strength. Faster spinning stars tend to have stronger magnetic activity and more energetic flares. That's reassuring, but not entirely conclusive. In 2012, researchers analyzing Kepler data reported superflares on sun-like stars that rotate at rates similar to the sun's. Historians still argue whether those stars are truly perfect solar twins or subtly different in ways that matter. Slightly younger, slightly more magnetically active, perhaps influenced by unseen companions. Then there's terrestrial evidence. Remember those mysterious spikes in carbon? 14 found in tree rings from 774 to 775 AD and 993 to 994 AD? These isotopic anomalies suggest intense bursts of high-energy radiation reaching Earth. The leading explanation is extreme solar particle events, possibly stronger than anything recorded in the modern era. If that's correct, it means the sun has already produced events more intense than the 1859 Carrington storm, just before telegraph wires existed to spark dramatically. The debate continues. Historians still argue whether those isotope spikes were caused by solar superflares, massive solar proton events without corresponding extreme optical flares, or even rare cosmic phenomena. But solar origin remains the most widely accepted explanation. You feel the scale of the uncertainty. The sun has been shining for 4.6 billion years. Your instrumental record spans barely a few centuries. Satellite data? Only decades. It's like trying to judge a person's temperament after observing them for a single afternoon. From what you know, the sun appears relatively stable compared to many stars. It doesn't exhibit the hyperactive flare behavior of younger, rapidly rotating stars. Its magnetic cycle is robust but moderate, yet statistical rarity is not impossibility. Scientists model the probability of extreme events using both stellar observations and geological proxies. Estimates vary, but some suggest that Carrington-level storms might occur roughly once every century or two, while significantly larger events could be rarer, perhaps once every 1,000 years or more. Historians still argue whether these probabilities are reliable or skewed by limited data. Rare events are notoriously difficult to model. The tail of the distribution, the extreme end, is where uncertainty grows widest. You imagine a true superflare erupting from sun. The initial radiation blast would reach Earth in 8 minutes. The associated particle storm could be intense. Satellites might experience widespread anomalies. Power grids at high latitudes could face severe stress. Auroras might blaze across nearly the entire globe. Would civilization collapse? Probably not. Modern infrastructure includes redundancies. Emergency procedures exist, but disruption could be significant. Temporary blackouts, satellite outages, communication interruptions. The key word is resilience, and that's precisely why scientists are watching more closely than ever, not because they expect imminent catastrophe, but because understanding the upper limits of solar behavior informs preparedness. There's also a fascinating twist. As the sun ages, its rotation will continue to slow, gradually reducing magnetic activity over billions of years. In the distant future, long after human timescales, it may become less flare-prone, but that's a comfort measured in eons. For now, you live under a middle-aged star, stable yet capable of mood swings. You tilt your head back again, imagining that immense sphere. It feels so constant in daily life. Sunrise, sunset, seasons turning. But beneath that routine lies magnetism capable of extraordinary outbursts. Historians still argue whether the greatest solar storm in human history has already occurred, or whether it's still waiting somewhere in the sun's tangled magnetic future. The truth is that uncertainty remains. And uncertainty in science is not fear, it's motivation. So telescopes stay trained on active regions. Isotope records are analyzed. Stellar analogs are studied. Models are refined. You don't watch the sun because you expect disaster. You watch because you respect scale. Because somewhere in its vast magnetic engine lies a potential for events you've never witnessed. And because understanding that potential is far better than ignoring it beneath a bright and deceptively gentle sky. You've contemplated superflares and ancient isotope spikes, and now your attention shifts to something quietly ambitious, building a planetary early warning system for a star. It sounds almost cinematic, like constructing a shield against cosmic fire, but in reality, it's a network, a collaboration, a lattice of spacecraft, ground stations, data centers, and international agreements woven together across continents. Because no single nation owns the sun. You begin at the L1 Lagrange point, about 1.5 million kilometers toward the sun from Earth. This gravitational balance point allows spacecraft to hover in a relatively stable position between Earth and the sun. Missions like SOHO, ACE, and SCAR have operated there, acting as upstream sentinels. They measure solar wind speed, density, and magnetic orientation before those conditions sweep past Earth. That 30 to 60-minute warning window is precious. But scientists want more. One proposal involves placing a dedicated space weather monitor at the L5 Lagrange point, trailing Earth in its orbit about 60 degrees behind. From that side angle, a spacecraft could observe active regions before they rotate into Earth view and track coronal mass ejections from a different perspective. The European Space Agency has advanced plans for such a mission, recognizing that side view imaging improves trajectory estimates. Historians still argue whether a full constellation of solar monitors at L1, L5, polar solar orbits, and perhaps even closer to the sun, would dramatically reduce forecasting uncertainty or simply refine margins. The debate often comes down to cost versus incremental improvement, but progress is real. Ground-based observatories remain essential. Networks of solar telescopes track magnetic fields across the visible disk. Radio observatories monitor solar bursts that can signal particle acceleration. Magnetometer arrays across Earth measure geomagnetic disturbances in real time, feeding data into global models. You imagine a digital map of the planet lit with tiny sensor nodes, each one quietly recording fluctuations in Earth's magnetic field. Together, they form a nervous system, detecting tremors from solar impacts. Then there's data sharing. Space weather is inherently global. A CME hitting Earth affects multiple time zones as the planet rotates beneath the disturbance. International cooperation has grown significantly over the past decades. Agencies share satellite data openly. Alerts are distributed across borders. The sun, indifferent to politics, has inadvertently fostered scientific diplomacy. There's something gently hopeful about that. You also see investment in modeling centers, supercomputers running magnetohydrodynamic simulations of CMEs propagating through interplanetary space. These models assimilate real-time observations, much like weather models on Earth. They estimate arrival times, magnetic orientation probabilities, and potential geomagnetic storm intensity. Historians still argue whether space weather forecasting will ever reach the precision of terrestrial hurricane tracking. The physics is different. The data sources are sparser, but the trajectory is clear. Better instruments, better models, shorter response times. Private industry has joined the effort as well. Satellite operators now maintain in-house space weather teams. Power utilities coordinate with forecasting centers. Insurance companies quietly assess geomagnetic storm risk in actuarial models. The watching is no longer confined to academic institutions. You picture a future where spacecraft orbit above the sun's poles continuously, mapping magnetic flux in 3 dimensions, where multiple sentinels at different heliocentric positions triangulate every major CME, where AI systems integrate all streams instantly, issuing refined forecasts within minutes. It won't eliminate risk, but it transforms a prize into anticipation. There's also research into hardening infrastructure itself, designing transformers more resistant to GIC saturation, building satellites with improved radiation shielding, developing protocols for temporary shutdowns that minimize long-term damage. Resilience becomes part of engineering culture. Historians still argue whether the greatest advances in space weather preparedness will come from better forecasting or from stronger infrastructure. Prediction reduces uncertainty. Resilience reduces consequence. Ideally, you want both. You step back and see the network as a whole. Spacecraft at L1 sampling solar wind, coronagraphs imaging CMEs, ground magnetometers tracking geomagnetic pulses, operators adjusting grids, astronauts sheltering, algorithms parsing images, international agencies sharing alerts. It's an ecosystem of awareness, and it exists because of a simple recognition. You live next to the star. For most of human history, that fact was poetic. Now it is operational. You feel the quiet hum of preparedness spreading outward. Sensors, satellites, servers, all tuned to the rhythms of solar activity. It's not fear driving it. It's stewardship. The sun will continue its cycles long after any one civilization fades. But right now, in this moment, you are building tools to coexist with its variability. Historians still argue whether future generations will look back at this era as the moment humanity truly became spacefaring. Not because you reached Mars, but because you learned to monitor and adapt to your own star. You glance upward once more. The same golden disk, the same steady warmth. But now you see the invisible web connecting it to Earth, a planetary early warning system stretching across space and soil. You are no longer simply basking in sunlight. You are listening for storms. And that listening, quiet and persistent, may be one of the most important technologies you've ever built. You've traveled from sunspots to super flares, from telegraph sparks to AI-driven forecasts, and now you return to something both simple and immense. You live with a star. Every morning, it rises without applause. Every evening, it slips below the horizon as if nothing extraordinary has happened. And yet, beneath that routine glow, nuclear fusion converts about 600 million tons of hydrogen into helium every second. About 4 million tons of mass become pure energy in that same second, quietly radiating across space, warming oceans, powering winds, feeding forests. The sun is stable on human timescales. That stability is the reason you exist at all. But stable does not mean static. You've seen how magnetic fields twist inside it, how poles flip every 11 years, how sunspots bloom and fade in butterfly patterns. You've watched flares erupt, CMEs race outward, auroras ripple over unexpected latitudes. You've followed spacecraft daring to skim its corona and satellites bracing for charged particles. Scientists are watching the sun more closely than ever before because, for the first time in history, your civilization is sensitive to its subtleties. In 1859, a geomagnetic storm made telegraph wires spark. In 1989, it dimmed a province. Today, it could ripple through GPS timing satellite constellations, aviation routes, power grids, and deep space missions. Not because the sun has changed dramatically, but because you have. Historians still argue whether modern society is fragile or resilient in the face of extreme solar storms. The answer is likely both. Fragile in complexity, resilient in adaptability. You have built an early warning system spanning millions of kilometers. Spacecraft hover at gravitational balance points. Solar imagers scan active regions. Magnetometers whisper about disturbances in Earth's field. AI models sift through magnetic hieroglyphs. Engineers rehearse contingencies. Astronauts practice storm shelter protocols. And still, the sun retains mystery. You do not yet fully understand coronal heating. You debate the limits of superflares. You refine dynamo models. You compare isotope spikes in ancient tree rings. The star at the center of your solar system continues to surprise you, not with malice, but with complexity. There's a humbling comfort in that, because even as your technology grows more intricate, you remain tethered to a cosmic engine older than life itself. You are, in a very literal sense, solar-powered organisms living under the influence of magnetic weather. You step outside in your mind and feel the warmth on your face. It feels steady. It feels benign. And most days, it is. Solar storms are not daily catastrophes. They are episodes in a long rhythm. The 11-year cycle rises and falls. The poles reverse. The corona shimmers. The solar wind flows. Over billions of years, the sun has maintained a delicate balance, bright enough to sustain liquid water, calm enough to avoid sterilizing its planets. That balance is extraordinary. Historians still argue whether humanity's increasing awareness of space, whether marks a turning point in how you see your place in the cosmos. Perhaps it does. You are no longer merely observing the heavens. You are managing risk beneath them. The watching is not an act of fear. It is an act of maturity. You acknowledge that your star has moods. You design around them. You study them. You adapt. And as you lie back beneath the night sky, knowing that even in darkness the sun is still shining on the other side of Earth, you feel something quieter than anxiety. You feel perspective. You are a species orbiting a middle-aged star, learning, slowly and perfectly, how to live with its magnetism. The sun will continue its cycles long after the day's satellites fall from orbit and today's grids are replaced. It will brighten gradually over millions of years. One distant day, billions of years from now, it will swell into a red giant and transform the inner solar system entirely. That's not tomorrow's problem. That's cosmic scale. For now, your task is simpler. Watch, measure, prepare, appreciate, because the same star that can rattle transformers also paints auroras across winter skies. The same magnetic reconnection that disrupts radio waves also fuels the solar wind that shapes the heliosphere, shielding you from deeper cosmic radiation. It is not enemy, not guardian, just physics. And you, small beneath its brilliance, have learned to pay attention. The sun rises, the sun flares, the sun reverses, and you, awake, curious, listening, rise with it.